Well, hello everybody. I hope you're all doing really well. Just want to say a quick thanks for all the nice comments that you've been leaving under the videos. Much appreciated. This week's little project is a HP 250 G8. Now, this is not turning on. It's got no hard drive. And as you can see there, I spent $56.50 on this. So what I'm going to do, I'm going to plug it in and see if we can power it on. I have my power adapter, my known good HP power adapter plugged in, and I press the power button. Okay. So we have got nothing at all. No lights, no screen, no nothing. Let's take out the motherboard and have a look.
Well, the first thing we need to check is whether we're getting voltage from the power adapter onto the motherboard. So the first section we need to look at is our DC in jack. So I'm going to take some measurements around here and see if we're getting power to the board. Now, as we can see, the cable that carries our voltage from our power adapter onto the board has two red wires here. So I'm going to take these as being our two positive input voltages, and these as our two grounds. One of these is probably the ID, and then I'm not sure what the other two do. But we just need to measure where those red wires hit the board. So what I'm going to do is introduce my multimeter in volts DC, place my black probe to ground, and take a measurement at the pin right here. And when I measure there, I find that it measures 19.66 volts. So our power adapter and our DC input jack are both good. I have a schematic for this motherboard, so I'm going to follow along the schematic and see where that voltage goes. As you can see here, pins 1 and 2 are where our input 19.66 volts comes in. The first components in line are these two parallel inductors, PL11 and PL12. If you look at my actual motherboard on the side here, you can see PL12, PL11. PL12 doesn't actually exist. There's only one inductor in the input. So what we want to do is just measure the other side of this inductor and make sure that there's no issue with it. When I take a voltage measurement after that inductor, I find it measures 19.66 volts, so that inductor is fine as well. So we're good up to this point. The next component is this MOSFET PQB11. Now I don't see this immediately around here. I think it's on the other side of the board, so I'm going to find it. Now I've gone around to the other side of the board and I've found PQB11, which is this MOSFET right here. As you can see, pins 5, 6, 7 and 8 are our drain pins, so I've marked those in D, D, D and D. And on the other side we have 3 source pins and a gate pin. So these are our 3 source pins and this is our gate pin. And as we're very familiar with at this stage, if the gate pin is high on this N-channel MOSFET, it allows our 19.66 volts through from our drain to our source. So what I want to check first is just to make sure that we have the 19.66 volts on our drain pins at pin 5, 6, 7 and 8 here. So I have my multimeter in volts DC. I place my red probe to any one of the drain pins. My black probe is on a ground and what I measure is 19.66. So we're getting our full voltage and we're all good up to the drain pins of this first MOSFET. Next I want to measure the gate pin of this N-channel MOSFET to see that it's getting the correct gate voltage to switch on. So I place my red probe to the gate pin and I find that it measures 24.80. So that seems good, and we just need to confirm that our 19.66 volts is now going through from our drain to our source. And taking a measurement at the source pins of that MOSFET, I find that there's 19.66 volts. So our voltage is getting through our first MOSFET and onto the pins of the second MOSFET. So this is PQB12, which is this MOSFET right here. I've zoomed in a little bit, hopefully that makes it a bit clearer. You can see that the path, as our voltage leaves the 3 source pins of our first MOSFET, it then goes on to the 3 source pins of our second MOSFET, which is also an N-channel MOSFET. So similar to the first one, we have a configuration of 3 source pins and a gate pin and then 4 drain pins on the other side. So I want to check the gate voltage here and see is this getting the appropriate gate voltage to switch on. So let's do that. Measuring in volts DC once again, I place my red probe to the gate pin of PQB12 and I find that it measures 25.54. So this is a high signal for that gate, so I would expect that our MOSFET is switched on and I would expect that we find 19.66 volts at the drain pins of this MOSFET as well. And when I measure at the drain pins of PQB12, I find that there's 19.66 volts there also. So what do we know at this point? Well, we know that our voltage to the board is good. We know that it's making it through our 2 MOSFETs, and that means that our main power rail is good. So I wasn't really expecting that because there was literally no signs of life on this laptop at all. No backlight, no LEDs, no nothing. But we've confirmed here that our main power rail is actually good. So we've confirmed that our main power rail is good. What do we need to check next? Well, the next thing to check is our always on voltages. There should be a 3.3 volts and a 5 volts always on power that's always available even if the laptop is switched off. So where do I find that? Well, I'm going to search on my schematic to see if I can find the IC that produces those voltages. The schematic for this laptop gives a nice block diagram here that is really clear and shows where all the voltages are generated and what are the ICs that produce them. So as we've already confirmed, we're good from the adapter, good right up to our main power rail, and as you can see, that main power rail voltage goes down to a number of different ICs where it's broken down to lower voltages. We're looking for our 3.3 volts always on. The only mention of 3.3 volts on this is 5 volt ALW and 3 volt ALW. Now these usually, even though they have the first three letters of the word always, the ALW ones are normally the switched higher current outputs for the 3.3 volts and 5 volts. But this IC is usually one package that produces two switched outputs and usually two LDO low voltage always on powers as well. So I think what I'm going to do is I'm going to locate this IC within the schematic and see if I can find where the 3.3 volts LDO is generated. And this is PU301. So what does this IC do? Well, this accepts 19 volts on the input. We know that our 19.66 volts main power rail is good, so I would expect to find that on these 4 pins. And then it produces two outputs by the look of it. It produces the LX one here, which is our plus 3 volts ALWP. So this is a high current 3.3 volts. And it also produces the LDO, which is called 3VLP. As you can see here, the 3.3 volts LDO is only good for supplying power of between 150 milliamps and 300 milliamps, so it's low enough current produced by this LDO voltage. But this voltage is the one that powers our Super I/O, and it's the one that provides power to our power button. So what I'm going to do is I'm going to locate this IC on the motherboard and take some measurements. And this is PU301 on our actual motherboard. To make it easier to follow along on this, I've taken the pins from our datasheet and I've superimposed them on the image here. So what we can see is we have 4 input pins right here. Now what am I expecting on that? Well, I'm expecting my 19.66 volts to be present on those 4 pins. And even though we're in essentially standby mode before pressing the power button, we should still have 3.3 volts on this LDO output right here. So what I'm going to check is, I want to check for sure to make sure that we have our 19.66 volts here, and I'm going to check to make sure we have our 3.3 volts on our LDO output. So with my multimeter in volts DC, once again I place my black probe to ground and my red probe to those input pins, any one of the input pins, and I find that it measures 19.66 volts. So we are getting our correct input voltage. Next I place my red probe to my LDO pin and I find that it measures 3.34 volts. So it appears that this IC is also working and it is giving us our 3.3 volts always on power. Having confirmed that we have our 3.3 volts always on power, I wanted to confirm that my power switch was actually working, and this is the power switch on that motherboard, SW1. So with my multimeter in volts DC, once again I took a measurement from all of the pins on this, and what I found was that when I placed my probe on this pin right here, it measured 2.34 volts. So I decided to press the power button, and when I pressed the power button that went to 0, and when I release the power button again it goes back to 2.34 volts. So our power button does appear to be working also. After confirming that the power button is working, we need to check the voltage around the Super I/O chip. First of all, it should be getting a 3.3 volts input voltage, and it should also be receiving the signal from that power button to tell it when to switch on and off. Now, because I have a schematic, it affords me the luxury of being able to look up what each of these pins are for. So I looked up the schematic and I've superimposed a few of those important pins onto our actual image here. So what I'm going to start with is measuring this capacitor right here. So we're going to take a voltage measurement at this. I place my black probe to ground, I introduce my multimeter in volts DC, and I'm going to place my red probe carefully to that capacitor. Now when I placed my probe to that capacitor, I found that it measured 3.34 volts, so it looks like we're getting a good input voltage on pin 124. The largest capacitor around this Super I/O is this one right here, which is connected to pin 9, and pin 9 from our schematic says it's plus 1.8 volt underscore PRIM. Now when I took a measurement from this, I placed my red probe to one side of the capacitor and it measured 0.00 volts. I also checked the other side in case I was getting the pin outs wrong, but both sides of that capacitor are measuring 0.00. Now even though I measured 0.00 volts on both sides of this capacitor, that's not necessarily indicative of there being a fault. I'm not sure if there's meant to be 1.8 volts on this when it's in essentially standby mode. So what I decided to do was power off the laptop, introduce my multimeter in diode mode, and just check to see if it was shorted or not. So place my black probe to one side of the capacitor and my red probe to the other side of the capacitor. I found that it measured short. Going back to our schematic, we can see this PU1801 generates an output voltage of 1.8 volts. It's labelled as 1.8 volt SP on the output after the inductor. Then it goes through one jumper where it's now called 1.8 volt underscore PRIM, and this is the rail that I think is shorted. So what I'm going to do is I'm going to locate this IC on the board. I'm going to try and inject voltage in here and see what warms up. On my motherboard image I have located PU1801, which is this IC right here. Now on the output of that we have inductor PL1801, which is PL1081, which corresponds to this inductor right here. And as you can see, if I move along the schematic, those two jumpers, one of which goes down to the shorted rail, are right here. So we've PJ1802 and PJ1803, which are these three jumpers, but they are connected to this inductor here. So what I'm going to do is I'm going to inject at this inductor and see if we can flush out the shorted component. I'm not even sure if it's even necessary. I'm sure you're all screaming out at the moment what's going to be shorted, but let's just inject and confirm. And just in case anybody is unsure as to how I hooked up that voltage injection, I introduced my DC power supply. I connect my black wire to ground. I connect my red wire to this inductor, which we saw earlier was PL1801. And I start the voltage low enough, so I start at 1 volt and I start the current at 0.1 amp or 100 milliamps and bring it up from there. And let's see what heats up.
And unfortunately, as I'm sure most of you predicted, the component that is shorted is in fact the chipset. As you can see there, the camera is slightly offset on this because it's pretty cheap, but there's only one area that is heating up, and that is the chipset.